1, 2, 3, testing.
Okay. Thank you.
So what, that's about 2 minutes slow, the clock. Okay, so thanks for inviting me to speak at your seminar. So what I want to talk about is sort of on the general theme of using geometry to create solutions to Diophantine equations. So big subject. Sort of the first example, at least that I saw, was the very classical one that on an abelian variety, for example, an elliptic curve, the k rational points where k is a number field, you analyze them using the group law, right, which is geometry. So I want to talk about a different class of varieties where we don't have quite as much structure as a group law, but there are some maps that we can use to try to propagate points. So the most classical example of this that I know of is the Markov equation. Which is the equation, well, it's this equation. So it's a surface in affine 3 space. Just so I can get an idea of, how many people have seen the Markov equation and played with it a little bit? And it's fine if no one has. Okay. Wonderful. Then you're in for a treat, because it's a very beautiful theory. So Markov studied this in the 1890s. And it came up because he was working on Diophantine approximation, which rational numbers approximate quadratic irrationals. Anyway, but I'm going to completely ignore the origins and just say, well, this is a Diophantine equation, and we're interested in the solutions in integers. And there are a couple obvious solutions. 0, 0, 0, which is a singular point on the surface. 1, 1, 1 obviously is a solution. But just from the shape of the equation, we can create maps which we can then use to generate new solutions. The idea is we have 3 projection maps. Right, we can project onto any 2 of the coordinates, which give 3 maps from M onto the affine plane, which are pretty clearly double covers. If I fix 2 of the coordinates here, I get a quadratic for the third. So I get 2 solutions. And the idea is, if I start with a point on M, and I consider the y0 and z0 as being fixed, then I get a quadratic x squared minus 3y0 z0 x plus y0 squared plus z0 squared equals 0. One of whose solutions is the x0 I started with, so I can just replace it with the other solution. And And very much like the way you derive the addition formula in elliptic curves. Anyway, so the two solutions add up to that. So we get an automorphism, an involution, in fact, I'll call sigma 1. Just given by this equation. And if I plug 1, 1, 1 in, I'll get 2, 1, 1. Okay, great, I've got one more solution. And then I can repeat this and get back where I started, which is not very interesting. But I've got 3 of them, right? I've also got a sigma 2 and a sigma 3, which just similar, except you switch the second coordinate or you switch the third coordinate, and they do not commute. So I can start using these, and you get this beautiful tree. Okay, so one other thing I want to point out, this is symmetric in x, y, and z, so I can always switch the coordinates. So I'm going to list the integer solutions with an increasing order of coordinates. And you can also change the sign of 2 of x, y, and z and get another solution with negative. So I'll ignore the negative ones for the moment, but in principle, we might want them. But anyway, so 1, 1, 2. Yeah, this I meant to bring with me and I left it on my computer. Well, actually, I guess we can do this. So 6, so I get 5, 5, 2, 1. I think that's the solution. Anyway, but then it starts bifurcating. And you get this whole tree of solutions. I was just talking with Kumar about how much better chalk talks are, I think, than slide talks. But the disadvantages in the slide talk, I put up a slide and you can see the first 10 layers of this tree. But you can Google it if you want. Okay, so theorem of Markov's from the I think it's 1880s, which is really very beautiful, is there's this singleton solution and every other solution can be obtained starting from 1, 1, 1 and applying automorphisms with the caveat I was mentioning. You can rearrange the coordinates, you can change signs. So let me sort of, all right, in this little corner here. I'm going to define G to be the group of automorphisms generated by the sigmas and generated by the permutations acting on the 3 coordinates, because you can always permute them, and the double sign changes. Which clearly are there. And Markov's theorem essentially says that all the solutions are 0, 0, 0, and the orbit of 1, 1, 1. This tree up to rearranging coordinates and putting in some minus signs. Yeah, that's a good question. I'm pretty sure that for this, yes, it is. For the K3s, I'm going to talk about, some of them actually have even more automorphisms. Okay. And by the way, I want to mention, this is a big group. Okay. If you just look at the group generated by the sigmas, It is actually a free product of 3 copies of Z mod 2, which is essentially the free product of 2 Z's. It sits in there with index 2, so yeah. So I tend to call it a big group. People who do algebraic groups say it's a small group because it's discrete, but for someone who's used to, you know, finite abelian groups, this is huge. Was there a question I saw? Ah, yeah. So that's what the group structure looks like. Okay, so we can generalize this a little bit to what are often called Markov-Hurwitz equations. Markov-Hurwitz surfaces or equations. And there are, well, you can imagine that there are lots of other things I can do. I'm just going to generalize it to this extent. Okay, I'll call that MAK. So I just replaced the 3 by an A and put on a little k. Now it's no longer true that, you know, there's just one big orbit with maybe one extra point or something. But what Hurwitz proved this is roughly 1910, I guess, is that there exists a finite set of solutions such that the entire set is given by these finitely many orbits. And this should look a lot like a theorem you probably know. It's a lot like the Mordell-Weil theorem, right? You have an infinite set of solutions to a Diophantine equation, but there's actually a finite generating set from which geometry gets you the rest of them. The proof has some similarities. It's much easier than the proof of the Mordell-Weil theorem. The Mordell-Weil theorem has 2 parts. There's proving A of k mod 2A of k is finite, or so-called weak Mordell-Weil theorem. And that you don't have an analog of that here. You don't need to do that. Then there's the height descent part, and that's exactly what's happening here. But it's a height descent, but the argument's a little different, and it's actually a little trickier than one might think. But anyway, oh, one other thing I want to mention, this is very much, these are theorems over Q, over Z. If you replace Z by the ring of integers in a number field, you no longer have finitely many orbits. In particular, if there are units in the ring of integers. Yeah, I don't remember. And I actually wrote a paper on that a long time ago. I meant to look it up, but yeah. Obviously, a very interesting question would be, you know, how many generators do you need? And I think that Gambard and Sarnak have a paper on that, where, I mean, sometimes there are no solutions. Sometimes, you know, what they proved was that, like, fix A, right? They probably took A equals 1. If you look at all the k's from 1 up to n, then on average, it needs log n quantity squared generators. So the number of generators does grow. So it's kind of a cool thing. But that's not what I want to talk about today. So here are 2 questions that people ask about these. And by the way, this is meant as introduction. What I'm aiming toward is we're going to do an analog for K3 surfaces of these Markov equations. So here's a question. What about finite orbits? I mean, if you start with 1, 1, 1 there, like, I mean, you get an infinite branching tree. There are starting points maybe where, you know, some of the branches curve around on themselves, but can you make it so that they all curve around on themselves? Well, 0, 0, 0 is a finite orbit. It's a singleton, not so interesting. Okay. And these have been completely classified. Yeah. Well, I mean, obviously a finite orbit, the coordinates will be in q-bar, but yeah. Even for the slightly more general case where, see, I mean, you can throw some more terms in here, you know, like bxy plus cxz plus dyz plus ex plus fy plus gz, right? I mean, if you put in terms that won't wreck the fact it's quadratic when you fix two of the variables. So they're much bigger families. And the finite orbits over C or over Q bar have been completely classified, even for the more general ones, but not that long ago. And the list is pages and pages and pages. And it's a very elaborate argument, which ends up having to, well, essentially, you end up with these linear equations that you have to find all solutions where the variables are roots of unity. That's kind of cool. And also, the last time I talked about this, I got several questions about what I'm about to say, so I'm going to answer it right now. I know nothing beyond what I'm about to write on the board with this. That these are related to algebraic solutions to Penleve differential equations. Somehow these finite orbits describe certain monodromy groups related to the algebraic solutions in algebraic functions. So that's kind of cool. And the second thing that there's been a lot of interest in recently is looking at the solutions over finite fields. So now there are plenty of solutions. And here I know how to classify the finite orbits because they're all finite, because there's only finitely many points. But now one's interested in the G orbit structure. For example, do you get a connected graph if you take the points and you connect 2 points if there's an automorphism connecting them? So this led to a few conjectures. First conjecture was due to Arthur Barriger, maybe 1991 roughly. This was in his thesis. He didn't actually put it in the article that he wrote about his thesis. So took some tracking down for people to discover it. But anyway, his conjecture was that if you take the original Markov equation and look at its solutions mod P, then, well, there's that silly 0, 0, 0 solution. But again, they're just, essentially, there should just be one orbit again. You can think of this as a local global question also, which is how many people think of it. Namely, that every mod P solution lifts to an integer solution because we know that this is all the integer solutions. So that's another nice way to think about it. That was in the 90s, and it kind of disappeared into the mists. Then Bourgain, Gambourg, and Sarnak, whose names are going to come up a whole bunch, so I'm going to just abbreviate it BGS. A few years ago, 5, 6, 7, 8 years ago, conjectured that something similar should be true. Yeah, I mean, I'm leaving minor conditions. Like here, you don't want P to be 2 or 3, because I mean, I got the 3 there. Here, you don't want P to be dividing the A and the K or anything. But if we fix, you know, an A and a K that are integers and start varying P's, that there should just be one orbit. Well, that can't quite be true. It's not even true for the original Markov equation. So the big orbit union small orbits with size independent of P. Okay, as P varies. So that's a pretty nice conjecture. What they prove, also very beautiful, actually they prove a whole bunch of approximations to this conjecture. So I'm just going to state one, but there are several other things. They prove that the number of points is the number of points in the biggest orbit plus, well, I guess the way they do it is plus P to the little o of 1 as P goes to infinity. And since, in other words, plus O of P to the epsilon roughly for any epsilon. And there are about P squared points on the surface. I mean, it's a surface mod P, so it has roughly P squared plus O of P points. So that's nice. And even more recently, William Chen by relating the solutions to a completely different problem, but only in the original Markov equation case, which is M30, or you can change variables a little bit, but this is that. So for the M30 case, he actually proved Barriger's conjecture, partly by using the tools that BGS had developed, and yeah, so proves Barriger's conjecture. And what he actually proves is that the number of elements in the big orbit is a multiple of P. It's divisible by P. And you can kind of see that having that and having the error of P to the epsilon, not immediate, but it's not that hard from this and using their tool, going through their proof to end up with Barriger's theorem, that there is no big orbit. I'm sorry, there is no small orbit. Well, there's obviously, I mean, it's a surface. Yeah, so you can use the Weil conjecture. Yeah, no, but actually, I mean, because this is quadratic, you can actually write down completely explicitly the number of points is P squared plus some stuff involving quadratic residues times P plus some stuff involving quadratic residues. It's a very explicit formula, yeah. Very elementary. Yeah. Any questions? Okay, good. So now let me throw all this away and go to the K3 analogs. Okay. So, definition. The thing is, these don't actually have a standard name in the literature, so we made one up. So they're sometimes called Weyler surfaces. So a tri-involutive K3 surface which we'll abbreviate TIC3s. Again, I'm not doing anything fancy. I'm just going to take essentially explicit equations. So I'll call this surface W. It's just a surface in P1 cross P1 cross P1 given by the place where a 2-2-2 form vanishes. Okay, so you just have something that's homogeneous in the x coordinates on this P1, the y coordinates on that P1, the z coordinates on that P1. Okay. If you start writing these down with the homogeneous coordinates, they look horribly messy. So I tend to write everything down using affine coordinates on each of these. So an example, which will be a recurring example through the talk, is very much like the Markov, actually, Markov Hurwitz. Where do I want to put the K? Okay. So there's an example of one of these TIC3 surfaces, a one-parameter family. And just so you realize, this is the affine thing. So this term really should be, x0 squared, y1 squared, y2 squared, because it's a dehomogenized, z1 squared, and so on. And we can do the exact same thing that we did with the Markovs, namely project onto two of the P1s, and that gives a double cover, and that gives involutions. Okay, so I have these three double covers, just projecting onto two of the coordinates. They give three involutions. And again, I can ask about orbits. But just to give you an idea what this looks like. So here's what the sigma 1 looks like for, so on the WK up there. Sigma 1 of x, y, z. Right. The y and the z stay the same because those are the ones I fixed. And I'm just switching to the other x coordinate. But if you plug in y and z, it's not monic in x anymore. Right, you got the extra thing. So what it ends up being, it's a little exercise. And you've got to work out what happens for points at infinity, blah, blah, blah. But anyway, of course, one thing is points that are integers in these affine coordinates do not stay integers. But it maps rational points to rational points, any field you're over. You'll be fine. So for example, and let you work sigma 3 out. So basically, well, in general, for most starting points, you're going to get a tree very much like the Markov tree. There tend to be an awful lot of rational points on here, so it's not like you're just going to get one orbit of rational points. Nonetheless, yeah, so remember I defined the group G, it was generated by the 3 involutions plus the other things. These don't necessarily have the other things, but I will, in a minute, look at the ones that do. So maybe I'll let G prime be the group generated just by these sigmas, which again is a free product of Z mod 2s. But in this case, there's certainly examples where they're more, a fair amount more. Yeah, however, I have a feeling, this is true. I have a feeling that for these surfaces, the automorphism group just has one copy of Z star Z in it, and you may get a bigger index, but yeah, I'm not even sure. Anyway, so questions, again, are to look for finite orbits over C in characteristic 0 or over Q bar, or the orbit structure over finite fields, or you can sort of mimic what happened with the original Markov equation. You could, for example, fix a point defined over Q and ask for how big the orbit is mod P as you vary P. So that would be a local global question again. To what extent can the mod P points be lifted to points that are in the orbit of this particular rational point? So again, you just have one tree. Okay. So this is quite a large family, even if you mod out by the change of coordinates on each of the P1s. So the first thing we did was we kind of restricted down to the ones that have the extra automorphisms kind of like the Markov surfaces. So silly proposition that has automorphisms. Well, the sigmas obviously, but also coordinate-wise permutations and double sign changes. It's just an exercise to check that these are the ones that have these extra symmetries. But I wanted to mention it because if anyone's interested in playing with these things, I think this is a more tractable family to play with. It's just a four-dimensional family, and up to isomorphism, it may even be less. I haven't checked. Anyway, oh right, the other thing, if not is this. And I also cheated a little bit up there. Even if the W is non-singular, it's possible that the involutions are not morphisms, they're only rational functions. On the other hand, there are singular examples where the morphisms are well defined everywhere. So you can play back and forth. Anyway, in this case, the sigmas are morphisms. If and only if, kind of thing you'd expect. There's a Zariski closed condition that's bad. Okay, so most of what we did was experimental. Oh, this is actually, couldn't have planned that better. Plus, our goal was to try to prove something like this BGS result, that there's one big orbit plus another orbit which is quantitatively smaller. And we have not yet managed to do that. And part of the reason, I think, is because the Markov equation, if you fix one of the variables, if you think about it, it's just quadratic in the other two, it's just it's a P1 minus couple, it's the multiplicative group. These K3s, if you fix one of the variables, you get a 2-2 form in P1 cross P1. Those are genus 1 curves, they're elliptic curves. So the BGS proof relies on looking at the action of the multiplicative group. And you can do the same thing here. You have the action of a section to this elliptic surface, essentially. But the multiplicative group, as you go from fiber to fiber, the number of points in the multiplicative group doesn't change because there is only one multiplicative group. But on the elliptic surface case, the K3 case, the number of points changes. And there's this somewhat delicate sum that they do, which is a sum over the divisors of the number of elements in the group, blah, 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 blah. And of course, this is just P minus 1 for every, right? But if I replace this by an elliptic curve, it changes from fiber to fiber. And anyway, we can't make the proof go through. But we did a whole bunch of experiments. So let me show you some of the results of our experiments. Yeah, one could try to maybe sort of do an average over P. Although the size of the groups is, I mean, if you assume the Sato-Tate distribution is true exactly, I still don't think the proof works. Yeah. There are other possible approaches, but yeah, it's interesting. Okay, so remember this one parameter family I have up here, parameterized by the k there, all right? I want to mention that wk is isomorphic to w minus k just by a change of variables, and also isomorphic to plus or minus I times k if your field happens to have a square root of -1 in it. So when we're looking at checking all possible k's over a finite field, I only have to check half of them or a quarter of them. So that's sometimes a little useful. Anyway, so what we decided we wanted to do was look for finite orbits in characteristic 0. Okay? And the way we decided to look for those was compile a whole bunch of data on the orbits in wk of fp, where k runs over fp star, well, or half of the values, whatever, the ones that give distinct things, okay? And look for interesting smallish orbits that appear frequently, and then try to lift them to characteristic 0. Because if you have a characteristic 0 thing, well, I mean, if it was defined over Q, then it would appear for every P. But if it was defined over, some cubic extension of Q, then it'll appear occasionally, depending for the primes that split. Plus, of course, you can get finite orbits just appearing for weird random reasons that don't lift at all. Plus, also, as I said, we were interested also in proving that there tends to be one big orbit here, and yeah, okay. So we compiled data up to primes up to about 80 using a program Paris that I wrote, which was fine. And then I rewrote it in Magma using one of the Magma packages, and it was a little slower. So I switched from using the permutation group package to the graph theory package, and it got faster by an order of magnitude, 10 times faster. And then switched to computing points on the affine variety and then throwing the extra points at infinity in separately, rather than using the built-in package to count points in projective varieties. And that added another order of magnitude. So we ended up about 100 times faster, which let us get up to 113, which it doesn't sound like maybe we even got a little further than that. But this was enough, looking at the number of orbits, to notice that when k equals 4, some of the primes had too large orbits, it looked, well, at least for these primes. Well, not all of them. It was for the primes congruent to 1 mod 8, and that's why we didn't notice it till we got a bit further, because there aren't that many primes congruent to 1 mod 8. Anyway, so experimentally, it seemed that there were too large orbits. And I talked about this at a conference, and Evan O'Doherty came up with this very nice explanation. And in fact, so if P is congruent to 1 mod 8, then, and you take k equal 4, it has 2 orbits of size 1/2 p squared plus O of p to the 3/2. It was a very, very clever idea. What he basically did was, assuming that your field has a square root of -1, he produced an invariant taking values in k star mod k star squared, whose fibers were about the same size, and the fibers were Galois orbits. Actually, I shouldn't have said, I don't mean an orbit, I mean 2 G invariant sets. It's possible those orbits break up into smaller orbits, but in any case, yeah. Oh, here, K actually would be any field. His invariant works in general. Yeah, oh, any field with I and K. And actually, you know what? It's possible you need a square root of 2 also. You either need a 4th root of 1 or an 8th root of 1. I can't remember which one. Yeah. And special to K equals 4, because a certain polynomial that he constructs, a discriminant, breaks up as a product, and he uses the 2 pieces. Yeah, very pretty. And it's on the archive. Okay. So I know that some of you want to go to a lecture that starts at 2:10. So what I'm going to do is talk until 2, and then we can take a 2-minute break for anyone who's heading out. But then I'm happy to stick around and show you some more examples or answer questions or whatever. So here's an example of the thing. What we found looking at a whole bunch of WKs of FPs is we found an orbit of size 144. And just looking literally at the points, looking at the data, getting our hands dirty, we found that there were points that looked like alpha beta minus beta for a whole bunch of primes. That was fixed by sigma 1. And if you applied sigma 3 to it, the third coordinate moved to 1. If you write down these conditions, and also the condition that alpha beta minus beta be on WK, you end up with 3 equations. In these 3 variables. And then you can check that if, even in characteristic 0, if you take alpha a root of this quartic, that determines K from this, and then beta is a root of this quadratic, then you get an orbit that then this point has a finite orbit of size 144. Needless to say, we didn't check that by hand, but okay. So we found a whole bunch of other 1-parameter families. I'm sorry. So this is a 0-dimensional family. In other words, it's a finite collection of Ks that has an orbit of size 144 that looks like this. So maybe I'll close just showing you a few 1-dimensional families. So if you look over the rational function field and take your K to be -2 t plus t inverse, there's an orbit of size 24. In particular, for every t you plug in, there's an orbit, okay? If you're willing to put a square root of -1 in then I times t squared plus t inverse, t to the minus 2, has an orbit of size 192. Okay. And the most interesting one that we found, maybe I'll even call this a proposition, though it's really just computational, is that there exists an algebraic curve of genus 9 and a k in its function field such that wk of points parameterized by coincidence function field has an orbit of size 288. And again, it was just, we saw a bunch of orbits of size 288 and started trying to lift them. And I don't want to give you the impression that you just find some mod p orbits and then you lift them and it always works. It usually doesn't work, actually. We found this one by looking at, I can't remember what the K was, but looking over a field with 53 elements. The same K with the field with 47 elements also had an orbit of size 288. And it turns out it doesn't lift. If you try to lift it, you end up with equations that are incompatible, except in characteristic 47. So at this point, it's kind of a hit or miss sort of thing. And we also have no idea whether there's any relations like with differential equations. I don't know of any. And finally, anytime you get results with sort of, finite orbits and things like that, one might wonder about uniformity questions. To what extent they're uniform bounds independent of the little k or of the finite field. Anyway, so as I said, I don't want to keep people from the other talk, but I'm happy to talk about that some more after. So, okay, thank you.